Imagine a world where your journey through space affects your journey through time. What if traveling at incredible speeds could actually alter the very rhythm of your personal clock? This might sound like science fiction, but it is a fascinating reality. To answer directly, yes, moving faster does indeed slow down your clock rate relative to someone who is moving slower or is stationary. This extraordinary phenomenon is known as time dilation, a cornerstone concept of Albert Einstein's special theory of relativity. The fundamental reason for time dilation lies in the constant speed of light for all observers, regardless of their own motion. Picture a thought experiment where light bounces between two mirrors. For an observer moving with the mirrors, the light travels a straight, short path. However, for a stationary observer watching the moving mirrors, the light must travel a longer diagonal path to hit the mirrors. Since the speed of light is constant for both observers, the light traveling the longer path for the stationary observer means that the tick of the moving clock takes longer to occur from their perspective. This difference in observed time is the essence of time dilation, showing that time itself is relative to an observer's frame of reference. While we do not typically perceive time dilation in our everyday lives due to our relatively slow speeds, it is a very real and measurable effect. One of the most common practical examples involves the Global Positioning System, or GPS, satellites orbiting Earth. These satellites travel at approximately 14,000 kilometers per hour, which is fast enough to experience significant time dilation. Their onboard atomic clocks run slightly slower than identical clocks on Earth. To ensure the extreme precision required for navigation, GPS receivers must continuously adjust their calculations to account for this relativistic time difference. The impact of this effect, though tiny at human scales, becomes profound as speeds approach the speed of light, or approximately 300,000 kilometers per second. This relationship is quantified by the Lorentz factor, which shows that as an object's velocity increases, its time dilation effect becomes more pronounced, eventually approaching infinity as it nears light speed. Furthermore, time dilation also affects subatomic particles in particle accelerators. Muons, for instance, have a very short natural lifespan, but when accelerated to near light speeds, their observed lifespan from our perspective is significantly extended, confirming the theory. Understanding time dilation is not just an abstract intellectual exercise. It fundamentally reshapes our understanding of space and time as interconnected aspects of a single reality. It highlights that time is not an absolute, universal constant, but rather a dynamic dimension influenced by motion and gravity. This concept is crucial for fields ranging from astrophysics to precision engineering, continually inspiring new technologies and deeper insights into the fabric of our universe.